Now it's coming, sir. Okay.
Is it okay?
Okay, sir.
Okay, till now you learned various
Class started,
AM
sir?
technologies and pre-processing, post-processing and DFAM. So today I will start one more module, that is AM, that is application perspective. Okay, so those who are interested in AM technology, so just they want to know how to use the technology and what kind of new and innovative products one can develop. Okay, just they want to know, they are very enthusiastic to know how to develop the new and innovative products by using various AM technologies. So that question no, we try to address in this module, that is AM for application perspective. So the AM technology is broadly characterized by two important applications, that is rapid prototyping and rapid manufacturing. Okay, this AM technology, it has been broadly characterized by two important applications, that is rapid prototyping and rapid manufacturing. So before going further, what is a prototype? It is a simplified model of what? Of a concept, of a model, right? So the word prototype is originated from the Greek word prototypon. Proto means first and typos means form, that is first or primitive form. Okay, and in simple terms, let us say designer he is trying to design a product or design a component of a product. Okay, so the prototype is the first physical representation or first physical model of the design that is being made by the designer. Okay, so they make this prototype model in order to test and evaluate the design. Okay, so in a typical product development, so initially a new product development starts with the design and then formation of the prototype. Okay, once the prototype is made, then it is being evaluated by the designer, as well as the prototype can also be sent for the evaluation to the customer. Okay, once the customer evaluates, and he will give the reviews, and if any changes are specified, they also propose the changes. Now all those changes will be incorporated in the design, and again the new prototype is made, and the updated prototype or the new prototype will be again send it to the customer for the evaluation, and if it satisfies, then the design will be finalized and the product manufacturing and mass production of the component can be performed or it can be initiated. Okay, and finally the the products can be deployed. So in simple terms, this is the typical the product development cycle. So here from this we try to define a prototype as an original, full scale and usually working model. In few cases, those are some kind of concept models. No, we don't apply any loads, and no, we can, it's not functional. Okay, it's only for concept. Validate the concept. That's it. And most of the times it is a working model or the functional model. Okay, of a new product or the component of a new product or the new component of a product or new version of existing product. Okay. So then, okay, with this introduction on prototype, we'll see what is rapid prototyping. What is rapid prototyping? What is rapid we define prototype, we understand what is prototype. Now what is rapid prototyping? Okay, so rapid prototyping is nothing but the group of technologies available for the designer in order to convert his or her design to the three-dimensional component relevant to the corresponding design. Okay, in other sense, the various technologies available for this rapid prototyping is additive manufacturing, CNC machining, and then injection molding. So the CNC machining and the injection molding, these are relatively expensive in long run when compared to AM. So nowadays AM is is a widely used manufacturing process for preparing the prototype or manufacturing the prototype. Okay, so that's the reason why we concentrated more on this additive manufacturing technology and corresponding application. And rapid prototyping is one of the important application of the additive manufacturing. So the general definition of prototype contains three aspects of interest. One is the implementation of prototype. Next one is the form of the prototype. The third one is the degree of approximation of the prototype. Okay, what is the implementation of prototype? So in other sense, the designer, he can go for a full scale model, full scale functional model, okay, or he can go for a subsection or a small or a component in a product, okay, to evaluate the function of that specific component. Okay, so in case of full scale model, full scale functional model, it can be used to examine if there are any outstanding problems or otherwise any unaddressed problems corresponding to the product before finalizing the design. So once the design is made, then prototype is made. The prototype, if it is a full scale prototype and functional prototype, okay, what they do is they test the prototype, and if there are any modifications need to be done, if any problems are unaddressed, then those will be addressed and the design will be remodified, okay, and this will continue till the design is finalized. For example, this is this chair. This is a full scale design, okay, and it consists of multiple components. So this full scale product can be manufactured and can be tested for its functionality before finalizing the design. Next one is sub-assemblies or components. Let us say I want to test the comfortable rest angle of this chair, okay, then one can go for the prototype of the platform, test platform, which can test this comfortable rest angles. Only the component, okay, it can be tested. Once it is tested, it can be finalized in the design. The next is the form of the prototype. Form of the prototype in the sense, it could be a virtual model or it could be a physical model. Okay, virtual model in the sense, virtual model is nothing but the digital representation of the physical model as well as its functionality. Okay, for example, a few people are working on the Formula car modeling, right, as well as the manufacturing. So you might be you might have faced a few problems with the distortion in the chassis. Chassis is it is nothing but the assembly of multiple components or multiple elements, like tubular components, let us say. So and all these components or all these tubular sections are assembled by welding, right. Now once you perform the welding, at the end, if you see the final assembly, it's not as per the required shape. There will be some form of distortion in the component or distortion in the final chassis. Okay. Now if you want to minimize the distortion, then one way is to go for the a lot of trial and errors. Okay, main importantly, there are two things which can affect the final distortion. One is the process parameters, and second one is the sequence of welding. Process parameters and sequence of welding. Okay, so now let us say you are assembling all the components, you have followed certain sequence, now you end up with some distortion in the final chassis. Okay, so now how can you avoid this? Because it's a time consuming process, lot of resources also involved. If there is a distortion, again you need to mitigate the distortion, which is very difficult task. Otherwise you need to do it from the first, okay, which involves lot of time, a lot of money, lot of efforts. So how can we minimize that? We can minimize that by using the virtual prototype. Virtual prototype is the digital representation. In the other sense, you go for the numerical modeling of the chassis development, okay, and then you simulate the welding operation at multiple multiple assemblies, okay. At the end you estimate the distortion. Now if there is a distortion, then you just try to change the sequence once again systematically, okay, and then you end up with the certain optimum welding sequence, which gives the minimum distortion, okay. All this testing can be done virtually in the numerical model, which is a virtual prototype, virtual representation of the physical model and its functionality, okay. And there is one more, there's the buzzword in the fourth industrial revolution, industry 4.0, is digital twin. Digital twin is nothing but the digital representation of the physical system. Let us say you have a you have a big turbine, okay. Now you are manufacturing that, and it is having multiple components, okay. Now once you manufacture that, you may find some problem, right, and then you want to know where the problem comes from and where do you want to change, okay. So if we have the virtual prototype or the digital twin for the final manufactured component, okay, and this digital twin can be developed by the huge amount of the data that is being generated from the physical system, physical model, okay, and the data will be used to develop the digital representation of the final component, okay. Now what are the changes you want to make, you can make here and try to see the final performance, and accordingly do the change in the final component. So in this way you will save a lot of time, lot of money, wherever the product development takes lot of time and which is expensive, there we can go for the virtual model. Another one is the car crash testing. It can also be simulated, okay. And on the other hand, the physical prototype is nothing but the physical model of your the physical component of your model, of your design, right. And if you go for the full scale model, you can go for which can be used subsequently for the testing and the and the experimentation, okay. So these are the two forms of the prototype, that is the virtual prototype and the physical prototype. Physical prototype, it's very straightforward. And the third important aspect of interest in corresponding to a prototype is the degree of approximation of the prototype. So this is the best example for this. You can very roughly represent the design or precisely represent the design. For example, this is the very rough representation of a multi-story building and its layout, okay. It gives the the general form and the dimensions of the envelope dimensions of the multi-story building, okay. This kind of rough representation can be used during the initial stage of the design, just to have just to feel the concept of the design. On the other hand, the exact application of the product, that is a full scale product, okay, which can be used for the evaluation and finalizing the design. So these are the three important aspects of interest related to prototype. Next one is the roles of prototypes. One is experimentation and learning, second one is testing and proofing, third one is communication and interaction, fourth one is synthesis and integration. Let's see one by one. One is experimentation and learning. So let us say I want to manufacture this product, okay, from the design to the final the final till the finalization of the design. You can make the full scale component, you can do the experiment, you can evaluate, you can change the design, okay. So this is one of the important role of the prototype. And if any questions or doubts regarding certain issues, for example, I want to optimize the footrest design. What I can do is I can go for multiple designs, I can make the corresponding prototypes, and then I can finalize the design. And what are the doubts are in the questions arise during the design, it can be addressed while testing and evaluation of multiple designs. The next one is testing and proofing. So this is one of the example, in the sense, during the initial stage of designing the spectacle frame, the glass frame, you can go for in the sense, you can make the component, and then you can test whether the linkage mechanism we are using, is it as per the design, or is it creating any trouble? If it is creating trouble, what is the trouble? What kind of modification that we need to do? That means, we are checking our design and we are evaluating our design. Okay. The next one is the communication and interaction. Communication and interaction. So one of the best example is the Auto Expo. In Auto Expo, the future cars, the models will be displayed. So now what will be the new designs proposed by the by the various companies? They are making the prototypes and they are displaying. So because it will, this 3D representation of 3D physical model, it is the best way of communication. Okay, it gives us the feel of what's happening in the model, what are the various features in the model, what are the advanced features. Okay, is it how advanced they are when compared to other models. Okay. So this kind of communication and interaction, this interaction also helps us in evaluating the product. For example, if any suggestions will be given by the by the consumers, it can be considered. If it is a valid suggestion, it will be incorporated in the final design. Such kind of communication interaction is also one of the role of the prototype. And the next one is the synthesis and integration. For example, this is the mobile set which consists of multiple components, and we assemble those things, right? So while assembling, we come to know, is there any problem while assembling, and once it is assembled, okay, is it functioning properly or not? Okay, that kind of testing can be performed. That is synthesis and then integration. That means, you try to synthesize all the components to make a single component, and while synthesizing and integrating, is there any problem while assembling? Okay, and once it is assembled, is it working properly or not? And if it is not working properly, what is the design flaw? This can be, this is one of the important role of the prototypes. So this rapid prototyping, is subdivided into two variants, that is solid imaging or concept modeling, and the second one is the functional prototyping. This rapid prototyping is subdivided into or subclassified into solid imaging or concept modeling and functional prototyping. So what's the difference between these two? Just from the name, can you guess the difference between these two? We discussed in the previous slides. Difference between concept modeling and functional prototyping. Mm-hmm.
Modification of the design based on the function. Based on our requirement, we can change.
Okay. Surya? Ajay?
The first one is similar to the original model by hand with the wings of geometry.
Yes.
While the second one has different properties.
That means you can you can put it for the service. You can apply the loads. Whereas in case of concept modeling, it only gives us the feel of the geometry. What are the CAD model we have? Once you print it, whether is it retaining the same shape or not, and the complete this three-dimensional interpretation can be done. So solid imaging or concept modeling, this is used to verify basic concept, and they cannot be loaded. Why? Because these are not functional components. And the scaled concept models are often used to verify this CAD model, and colored models are valuable tools for concept evaluation. In the sense, so let us say this is the concept model for the rooftop corresponding to this car. Okay, anyway, you can't use it here. Just it gives us a feel of the final shape as per the design. And it's also possible to have different colors for different components. and if you have different colors for different components, it is easy to judge, okay, this color component is having the defect. This is easy for judging. Next one is the functional prototyping. So here this is the the actual product, that means in the sense the prototype which you can put in the service, put it to the service, okay. For example, this is the functional prototype of adjustable air outlet grill for a passenger car, and this is manufactured by stereolithography, okay. So here you can put it to the service, you can test it, you can put it on the car and you can test its functionality, and if there is any flaw, it can be it can be rectified in the final design. So till now we are discussing about the prototyping. So the next important application for this additive manufacturing is the manufacturing, right? That is rapid manufacturing. It is again subdivided into two variants, that is direct tooling and direct manufacturing, okay. So what's the difference between direct tooling and direct manufacturing?
Direct tooling is about making molds for the parts.
Molds for the parts, okay.
Manufacturing is
Direct manufacturing components, excellent. So direct manufacturing, here as he already said, we directly manufacture the final functional component by using AM. It's not prototype, it's the final component that we put it to the service, that we assemble in the component, into the product, okay. So for example, this dental implants, okay, these are typical cobalt chromium alloy made dental implants by using SLM process. So and these dental implants are directly used for the service, okay. And this one more example, this is the direct manufacturing of the aircraft engine cover hinge, okay, and this is the corresponding optimized model for the in the sense this is the corresponding optimized model after topology optimization, okay. So it is used, it is easy to make this this engine cover hinge by using machining, but here it is very difficult to make this, but this complex shape can be manufactured conveniently by using AM process, okay. This is the flexibility given by the AM, that means this kind of bionic structure, complex structure can be manufactured comfortably by using AM process, in contrary to the conventional machining process, okay. So these are the final components that we directly use for the service, and these components are directly manufactured by AM process. Next one is the direct tooling. Under direct rapid manufacturing, one variant is a direct tooling. Here what are the tools, that is the molds and the die and the mold inserts, okay. So all these are directly manufactured from AM process by using AM process. For example, you know this die casting process, right? So in die casting process, just for continuity I am playing this thing. So as you already know, it is having two metallic dies. This is a fixed die and this is a movable die. Sorry. So this is the fixed die and this is a movable die, and this is the this vessel is having the molten metal, and this molten metal is being filled into this tube. Once it is filled, this lid is closed, and with the help of this ram, the molten metal is being entered into the junction. That means before sending the molten metal, these two molds or these two dies, these two are assembled. Once it is assembled, the junction gives the cavity which resembles the shape of the final component. So here the molten metal is being, so these two dies are assembled and then molten metal is being injected into this cavity. Okay, once it solidifies, it gives the final component, right. So this is the component, this is the extra material that need to be taken off, that means you need to cut it off. Okay. So now here the thing is, let us say if we are making these two components, final two components, if these two components are manufactured directly by additive manufacturing, then it is called as the direct manufacturing. And these two dies, these are used for the die casting. So these are the tools. If these tools are manufactured directly by additive manufacturing, then it is called as the direct tooling, in simple terms. For example, this is the the set of the dies. Okay, this is the component to be manufactured, and these two dies, these are manufactured by AM process. Okay, depending upon the size of the component, we need to choose the suitable AM process. For example, here the die size is more. Okay, so here what we go is, we can manufacture this by using wire arc additive manufacturing. That is the a high productive variant of the additive manufacturing. Okay, so and these are the mold inserts. These mold inserts can also be manufactured by AM process. Okay, direct tooling. So one more important the application of this direct tooling is to make the very complex dies having the conformal cooling channels. If you want to make this die with the conforming cooling channels, it is very difficult to do by conventional process. Okay. On the other hand, with the AM process, we can comfortably manufacture the dies with complex conformal cooling. Conformal cooling is nothing but here the cooling channels are it is been arranged within the die, okay, surrounding the mold cavity, okay, in such a way that the heat will be taken out from the component, solidifying component uniformly. Okay. So these are the conforming cooling channels. And this is one more example. This is a steel mold for manufacturing the golf balls. So you can see the cooling channels here within this mold. We can manufacture this by using this DMLS process, direct metal laser sintering. Okay. So just for some information, this video gives you the some brief information about the conformal cooling channels. This is the component to be manufactured, and these are the dies. So the cooling channels are arranged within the die in such a way that the heat should be dissipated or should be taken out from the solidifying component uniformly. Otherwise, it leads to metallurgical defects. See the complexity of the conforming cooling channels. Again, these are the two dies. This is the component to be manufactured, and accordingly, as per the shape of this component, the cooling channels are around within the molds for the uniform heat extraction. So the this prototype tooling, it is between the prototyping and manufacturing. So when do we go for this prototype tooling? So here if you want to manufacture some few components, If you want to manufacture more components, then you can go for direct tooling. There, we can use the metal, and this metal molds can be used to manufacture multiple components, long batch, large batch, okay, of 10,000 or 20,000 components, depending upon the complexity and the metal used, okay. Now, if you want to manufacture the prototypes, okay, for that, if you want to make the tools, you can't go for this direct tooling. You can't go for the expensive metal tools. Okay, it is not economical, because let us say if I want to manufacture some for 5 or 10 prototypes, then I can't go for this direct tooling. Okay, here in place of metal, we'll use some inexpensive material, however, which is capable to manufacture some small 5 to 10 components depending upon the requirement. Okay. So here, this in prototype tooling, the limited run of parts can be produced to test both the functionality of the tooling as designed and the precision of the parts it yields. That's what we discussed. For example, here this is one example of prototype tooling. So this is the this rubber boot sole mold. It is made of polyamide instead of metal. The material used for the mold is polyamide. It is relatively expensive when compared to the die steel that we use for the metallic molds. Okay, so here this is capable to manufacture these prototypes of limited number, prototypes in limited numbers. Okay, and this is one more example. So this AIM injection molding, so the process in the sense these mold inserts are used in AIM injection molding. We will see it in the subsequent slides. So these are the mold inserts which is manufactured by stereolithography. Okay, we will see what is AIM injection molding. So prototype tooling and direct tooling, these two comes under rapid tooling. Rapid tooling is characterized by two variants, that is prototype tooling and direct tooling. So these two we call it as these two comes under the rapid tooling. Whenever I say rapid tooling, these two comes under you should should have these two in your mind. So rapid tooling. Okay, so here the important term is the rapid tooling. So again, this rapid tooling is subclassified into various variants. One is soft tooling and hard tooling. Again, soft tooling is subclassified into direct soft tooling and indirect soft tooling. Similarly, hard tooling is subclassified into direct hard tooling and indirect hard tooling. We'll see what is this. You'll see all these things in detail. First one is direct soft tooling. Can you guess something? What is direct soft tooling? Direct tooling. In rapid prototyping, we have direct tooling and rapid prototype tooling, right? So direct soft tooling. What is direct soft tooling? Any guess? Making similar kind of products, okay?
Tools for similar kind of products without much bigger change in the products.
Okay, and so one example of this direct soft tooling is molds for liquid metal sand casting. In sand casting, we prepare molds. We use the green sand and we prepare the molds, right? Mold cavity with the sprue and the riser runner. Did you remember? Right. So here these molds can be 3D printed. The complex molds, complex cores and gating system can be 3D printed and comfortably used directly to manufacture the complex components. However, once you make that mold, we use it only once. Once the component is made, you need to break it and take the component out. right? The second one is the composite molds. In the last slide you have seen AIM injection molding inserts. So those mold inserts are the composite mold inserts. No, it is made of a relatively soft material and it is made of stereolithography, and this is used in injection molding of plastic components. And these molds, these molding tools supports a single or small batch production. Here, we can use this this set of composite molds to manufacture 100 to 1000 components, depending upon the material we are using. Okay. So these two comes under, these are some two important examples under this direct soft tooling. For example, so the direct soft tooling examples are selective laser sintering of sand casting molds, we have seen in the last slide, and direct AIM. So let's see what is this, the selective laser sintering of sand casting molds. This video demonstrates about the process, about this example of direct soft tooling, that is the selective laser sintering of sand casting molds. So this is the engine block, it can be manufactured by using sand casting, and here we use the molds and the cores which are 3D printed to make the casting process, in the casting process. So we have the cores, similarly, one layer of the sand is being spread, and then laser melts the sand particle coated with the binder. Here the sand particles are coated with the binders, and those binders are melted by the laser. Once it melts and solidifies, it binds the sand particles, and the laser melts the sand particles as per the given what? Given tool path orientation. Okay, yeah. Again here, layer by layer, the same technology. Selective laser sintering. Here the material is the sand particles with binders. That's it. So these are the molds, 3D printed molds. Similarly, cores can also be manufactured by selective laser sintering with all the features required, complex features. These are the cores. And all these are assembled. Cores are assembled with the molds. We pour the molten metal. is been placed in a container with backing sand. This is the final casted product. This is the final casted product. And it's not only for the cast iron, also aluminum casting can also be manufactured. Okay, so so now you have seen the complete procedure is already explained here. You have already seen, it's documented here. No need to explain this slide. Here, whatever the accuracy we get here, it is equivalent or better than the sand casting, normal sand casting. The second important example under direct soft tooling is direct AIM. That is AIM refers to ACES injection molding. ACES is accurate clear epoxy solid. So these are the mold inserts made of epoxy, and that is the resin molds, and this is made and this is manufactured by using steel lithography. And you can use that means you can fill this cavity by various materials like thermoplastics, aluminum filled epoxy, ceramics, and low melt temperature metals. Okay. However, we can use it for only limited numbers. We can't use it for batch production, for mass production. Okay. And here the accuracy levels are very good. So we have seen a direct soft tooling. Now we'll see a direct hard tooling. Now can you guess what's the difference between direct soft tooling and direct hard tooling?
More components.
Yes, these are metallic molds, and you can manufacture more number of components. So here we can go for selective laser melting, and depending upon the size of the molds you require, we choose the suitable AM process. These tools are used for high volume production. So these are some examples of direct hard tooling methods. One is rapid tool, DMLS tooling, laminated metal tooling, and pro metal TM rapid tooling. So we have seen all these processes. These are all various AM technologies. In simple terms, these are the various AM technologies that can be used, and here we are using it for manufacturing the tools. Okay. In rapid tooling, here this technology is developed by DTM Corporation, and here they use selective laser sintering process to make the component. And what are the mold inserts prepared under this rapid tool? It's used for high volume production. And laminated metal tooling. So we studied about loam process, right? So the same technique we use here to manufacture the tool, okay, as per the design. And the next one is a DMLS tooling. Here this technology is developed by EOS. Okay, here the same technology, in the sense it is the same laser sintering process. Okay, but its commercial name is given as DMLS. So these are all self-readable, in the sense no need to explain this. So I'm leaving this for your self-study. Pro Metal Rapid Tooling. Pro Metal Rapid Tooling. So we have seen soft tooling, hard tooling. In soft tooling, direct soft tooling and direct hard tooling. Okay. Now let's see no, indirect soft tooling and indirect hard tooling. Indirect processes. So before going to discuss about the indirect processes, let's try to see a few disadvantages of the direct AM process, the direct processes. Okay. So here one of the disadvantages is machine dependent materials. We are directly using the AM process to manufacture the tools, right? And each machine, depending upon the make of the machine, the materials allowed by those machines, those are limited. Okay, so these machines are material dependent. They doesn't allow all the materials, only specific materials are allowed. And then a restriction in terms of color, transparency and flexibility. You don't get the materials of different colors. We can't use the materials of different colors. If you want the components having different colors, then different transparency and flexibility, then it's one of the disadvantages. And almost no cost reduction with an increased production volume. Okay, for low volume production, AM is suitable. Okay, but as the volume increases, then there won't be any reduction in the cost. In contrary, the conventional CNC machining and injection molding, for low volumes, it is very expensive. But as the volume size increases, there's the number of production, the production quantity increases. Okay, the overall cost will be decreased. Okay, this is one disadvantage. So how can we overcome these disadvantages? So it can be overcome in indirect processes. So here what we do is, in simple terms, we make the master pattern by using AM process, and we use this master pattern. Okay, and this master pattern is having the geometry exactly equivalent to the design we are making, right? So what are the master pattern we are preparing by using AM process? It is having the exact dimensions of the design. Now we have the component with exact dimensions. Now we use this pattern, master pattern, to make the components incorporating the required properties, for example colors and transparencies, okay, by using some reproduction process or copying processes. And this copying process, again, these are not AM processes. We will see what are those reproduction processes. Again I repeat, here we make the master pattern having the exact dimensions in the design by using AM process. We take this master pattern and we try to produce the multiple components, or we copy this component by incorporating the required properties like color, transparencies by using certain secondary reproduction processes. We will see this. Here the process is quick. The reproduction processes that we are going to discuss, those are very quick. And here why we call it as indirect process, here we are not using the layered manufacturing to copy the component. However, the master component is manufactured by AM process. Okay. It is also called as indirect rapid prototyping process or secondary rapid prototyping process. So it comes under one more vertical, that is the non-additive processes. However, it is linked to the additive manufacturing. In the sense, the master pattern from the AM, and we use some non-additive process to copy that master pattern, incorporating the required properties in the copying elements. So one important example for this indirect process is the room temperature vulcanization or the solid rubber molding. Okay. This video demonstrates the solid rubber molding. It's very simple. this is a silicon mold and this is the component manufactured. We use this silicon mold to produce multiple components. We will see how. Let us say initially we make the master pattern by using AM process, and then we prepare the silicon mold by using this master pattern, silicon mold with the cavity, and then we pour the polymer material, liquid polymer material, polyurethane, into this mold cavity, okay, and once it gets solidified you get the component. So initially the master pattern is manufactured by using AM process. So this is a master pattern. Now it is been coated with for proper surface finish, and then we place it within a box and pour the polyurethane, it's polymer material. So in the sense silicon rubber I can say. It's not polyurethane, it is silicon rubber. The silicon rubber we pour it, once it gets solidified, okay, you just try to split it and take out the master pattern so that you will get the cavity within the silicon mold, silicon rubber mold. So this is the cavity. Now you use this cavity to produce multiple components. Now you pour the polyurethane material having different colors, you mix with different colors, pour it and manufacture that. So now we are pouring the polyurethane material, it is being filled within the cavity, you just bake it at around 70 degrees centigrade for around 3 hours, and then you take it out. So this is a component. So this is a copied component from the master pattern with required required properties, for example different colors. This is a assembled component. So however, now we use this silicon mold to manufacture only limited quantities. For example, some 20 to 30 components before it starts breaking. So this figure explains the complete working principle. So this figure explains, figure A explains producing the silicon mold. So we place the AM master pattern within the box, and then you place the sprue, and then pour the silicon rubber, and then you bake it at certain temperature for some time, so it can get baked, and then you take out the silicon rubber, and then split it at the center, so that once you split it, take out the master pattern, so that it generates the cavity within the silicon molds. Once you assemble that, you will get the complete cavity which resembles the shape of the component you are going to manufacture. Okay. So and then you place the funnel, and then pour the polyurethane material. Okay. So that is the material of your casted product. Okay, or the copying product, copying component. Okay, you pour it, and then you cure it, and then take disassemble the two solid molds, two silicon rubber molds, and take out the component. Okay, so we use this silicon rubber molding in manufacturing the functional plastic, metal and ceramic components. Okay, however we use this under vacuum in order to avoid the entering of the air bubbles into the mold. So this is the indirect prototyping.
Sir, in sand casting also we prepare the pattern first and then only we prepare the mold, right?
Yeah.
So difference is we can manufacture ceramic metal.
it will also come in the subsequent slides. Okay. So these are some of the examples. So this indirect prototyping is, this silicon rubber molding comes from indirect prototyping. Indirect prototyping. Here we are using the AM pattern, master pattern, to copy it to multiple components. And these are some of the examples. For example, this is the master pattern, and these are the multiple copied patterns with different colors. And here also, this is the master pattern, and these are the various copied patterns, copied components. Next one is the indirect tooling. Indirect tooling. So till now, do you have any queries? Do you have any queries up to this point? Hardik? Vidala? So we talked about indirect soft tooling. Now, in the sense, indirect hard tooling. So yeah. So in case of indirect soft tooling, we the master pattern is prepared, and the master pattern is used to make the multiple components, okay, by using such as silicon rubber, epoxy resin, these things. And few available important indirect soft tooling methods are, one is arc spray metal tooling, and silicon rubber molds, and then castings, in casting, sand casting, investment casting, and then evaporative pattern casting. Okay, so we are talking about the tooling, indirect tooling. Okay, so one is the first important example, is important method is the arc spray metal tooling. So here, initially we get the master pattern. This is the master pattern. Okay, that is being manufactured by using AM process. What you do is, you just fix it to the base plate, and then a coating is made over the surface of this pattern. How do you make that coating? By using, the metal spraying. So these are the two electrodes. These are the two consumable electrodes. Arc is formed at the junction. As a result, metal is melted, and this molten metal is being sprayed, with the help of the gas, high pressure gas. Okay, so the metal is being sprayed over the surface of the master pattern. Okay, so now the metal is being sprayed over the surface of the master pattern. Okay, and then you place it inside a container, and then you fill the container with the appropriate backing material. Okay, the backing material could be epoxy resins or low melting point metal alloys and ceramics. And you just reverse it, take out the base plate, and keep the other half of the master pattern. And then again repeat the process. Do the metal spraying, then place the container, keep the backing, and then disassemble these two containers, take out the pattern. So now this is your tool, your molds with the cavity. In this way, you can make the indirect indirect soft tooling by using arc spray metal tooling. This is one of the methods to manufacture the tools, injection mold tools, okay, indirectly using the AM master pattern. So this is one of the example, the zinc molding die for a fan blade. So these two molds are manufactured by using arc spray metal tooling. Next one is silicon rubber molds. The principle is same as we discussed in the earlier slides. And then the casting, sand casting. So in sand casting, you already know all these things. It's a basic sequence, a basic procedure in sand casting, right? So the pattern what you use here, it is a master pattern. It is manufactured by using AM process. And so let's say this is a pattern. Here it is manufactured by using AM process. And the next one is the investment casting. You studied about investment casting, right? What's the principle? What's the principle of investment casting process? Okay. How do you produce multiple components? By using wax pattern, right? So this is the sequence. Initially you need to prepare the wax pattern. For that we require the mold separately, which is an additional job and expensive. So what we do is here, we try to make the wax pattern by using AM process. Okay, what are the pattern we are using? It is made by AM process. And the remaining the steps are same. This is very important here. The next one is the evaporative pattern casting. Here, this is a foam pattern. This foam pattern is additive manufactured, and it is being sprayed with the refractory compound, and then we place it within the mold box with the backing material, and then we pour the molten material. Okay, as the molten material is being poured, the foam will be evaporated, and the place where it is evaporated is being filled by the molten material. Okay, in this way, it continues till the complete foam is being evaporated and the complete cavity is being filled by the molten material to make the final component. Here again the pattern is being made by using AM process. So this is the indirect tooling. So we discussed indirect prototyping. What is an example of indirect prototyping? Silicon rubber molding. And indirect tooling we discussed arc spray and various casting processes. Okay. If you have any queries, you please ask. Finished? So it may require another 20 to 25 minutes, so we can finish this module, and then we can start with the materials part with the AM process. Okay. So coming to the materials part, AM is nothing but the welding process only, right? Instead of joining two places, we are joining layers, layer upon layer. So we start with some basic welding metallurgy, which is applicable for the AM process, and then we can see in detail about various metallurgical challenges and metallurgical aspects related to AM process. Whether it is okay. Okay then. Yeah. Thank you.
About coming up exam syllabus.
Syllabus.